Good evening, everybody. My name's Kristen Fletcher. I'm the Program and Outreach Coordinator at the Hailey Public Library, and I'm so delighted that you could join us tonight. Tonight, our talk will be Smart Power, How Microgrids Bolster Energy Resilience, and our presenter is Dr. Manish Mohanpurkar. These smart microenergy systems are designed for remote communities like ours, with the intention of diversifying electrical supplies and ensuring resilience. I wanted to take just a moment before I do a more formal introduction of Dr. Mohanpurkar to tell you a little bit about what's happening with the Hailey Library. We get asked a lot when we're going to open our doors for general browsing, so we're not quite there yet. We are now open Monday through Friday, 10 to 6. For holds, you can put a hold on through our website by calling us or by coming to the front door, and we'll process that for you. It usually takes about an hour once we get your request, but we're getting a lot of people taking advantage of that service, which we're pretty delighted about. Our drop box is now open 24/7, so if you have books that maybe you've had through the whole virus pandemic and ready to pass them along back to us, that drop box is open now. A couple of upcoming talks that you may be interested in. Tim Frazier, who is a very popular speaker and astronomer, is going to do his second of a 4-part astronomy series, Constellations Spring into Summer. So if you've always had an interest in learning about the constellations and our beautiful dark skies, this is a terrific program to tune into. It too will be Zoom. The last program we had with Tim was just absolutely terrific. He's a great presenter and always has terrific slides and stories. And then on Thursday, June 25th, we're bringing in nationally recognized historian Dr. David Adler. His specialty is constitutional law, and he's going to be talking about women's suffrage and the passage of the 19th Amendment, because we're celebrating this year the right of women to vote, which just seems pretty remarkable that there was a time when we weren't considered capable of casting a vote. So we want to celebrate that, and we here at the Hailey Public Library are thrilled to have Dr. Adler with us. And then there's going to be a follow-up series of presenters on remarkable Idaho women back in the day. So tonight's talk is the second of 3 talks that we're partnering with the Idaho National Lab. The first one, many of you may have attended, was the future of electric vehicles. And then in September, we're going to do a presentation that celebrates the landing of the Mars rover Perseverance and the INL's role in getting it to Mars. So that should be a lot of fun. So keep an eye on that. The information will be on our website and in press releases, and we'll send out an e-boost, which is a really good way to find out about our programs. So just an overview of tonight. As everybody entered, you were all muted and the video was turned off. But we really want this to be an interactive program as much as possible. So there's a questions feature that you can choose and type a question into the bottom. That questions feature is like a chat feature, will be monitored by 2 of us, so we don't miss any of your questions. And I'll ask Manish as many of the questions as time allows, and don't hesitate to ask questions. We really are looking forward to that. This talk will be recorded like the last one was, and a link will be sent out a few days after the event. We'll also take a few minutes at the end of Manish's talk to gather your feedback and suggestions for future programs. And I'll remind you of that as this program draws to a close. But we really are interested at the library to find out what you're interested in, what kind of topics you'd like us to bring to the community. Maybe you know speakers that would be terrific speakers to share with our community. So we really rely a lot actually on hearing from you. And I will say that this series is as a result because my friend Paul Reese went on a tour at the INL last summer, and he came back and was so impressed by the work that the researchers at the INL were doing. And he introduced me to them. He introduced me to Abby Todd, and Abby and I have been working together now for 3 or 4 months to bring these programs to our communities. So I want to thank both Paul for the idea and the introduction, and Abby for just being such a terrific person to work with through these programs and through these various technologies. So right now, it is my great pleasure to introduce Dr. Manish Mohanpurkar. He works broadly in the area of power and energy systems. His research includes power systems analysis, real-time digital simulation, power markets, assimilation of renewable energy, and energy resource planning studies. In addition, he has authored more than 45 technical papers in leading scientific publications. He holds a doctorate in electrical engineering from Colorado State University, a master's in electrical engineering from Oklahoma State University, and a bachelor's in electrical engineering from Government College of Engineering, Aurangabad, Maharashtra, India. So please, we can't applaud and hear you, but please join me in welcoming Manish. Thank you so very much, Manish, for joining us here tonight.
Thank you, Kristen. That was a very nice introduction, and you said my name very correctly, so I appreciate that personally.
Thank you. I did do some practicing, so.
So good afternoon, everybody. As Kristen mentioned, I'm super excited to be here, and I want to have a conversation with all of you on how microgrids have helped us in the past, how they're helping us currently, and a little bit on what the future holds as far as this technology goes for us in order to add energy resilience to our communities and our cities. So so Nicole and Abby have helped me create a nice set of slides to present and help have a discussion on this. So please feel free to use the questions feature that Kristen just mentioned, so that I get to know that there is an interest in this topic, and I'm able to convey some of the information and experiences that I have had professionally working in this technology for the past several years. The two pictures that you see on this particular slides are some of the work that we've done in the lab, and it's actually my picture with a particular type of simulator that we've used for studying microgrids and taking measurements and using controls and things like that. Just doing a lot of science and engineering at a very high fidelity to get the right answers that we are looking for. So I've been working at the Idaho National Lab for about 7 years as a power system scientist. So I wanted to definitely cover and give a background on what is Idaho National Laboratory. Idaho National Laboratory is one of the 17 Department of Energy laboratories that conducts R&D in areas that are extremely important for us as a nation. As the name suggests, all these labs are involved in understanding and synthesizing energy in some or the other format. We do things that are extremely difficult, they're costly, and at times risky as well for the industry out there to undertake, or even the academia. So we do research in sort of an early level of research before it gets into commercialization. So it is that space that we fill that helps realize technologies from just concepts to technologies being commercialized and widespread in the society. Idaho National Laboratory has two physical locations, if you will. If you look at the right picture in that inset, one is referred to as the INL site, and the other one is referred to as the Idaho Falls. So in Idaho Falls, we have quite a bit of administrative offices. I myself work from the Idaho Falls office. There is quite a bit of a lab space as well, and we do a lot of research in the city offices, if you will, regarding electric grids, biofuels, electric vehicles, advanced manufacturing, even some nuclear research related R&D as well. On the site, it's a much wider area. It's a significantly large area. INL is approximately 890 square miles of area, so there's a huge area out there that is used for doing a lot of technical experimentation of different things related to nuclear energy. There is also a significant component of the electric grid that is used for experimentation out there at the site. So these two locations work together to, and they constitute the Idaho National Laboratory. So they help us solve a lot of cutting edge energy-related challenges. And I'll be explaining what sort of problems we try and solve. And today we'll focus mostly on microgrids. As you can see on the left side, we have shown a map of all the Department of Energy National Laboratories. There are 17 of them. Each one has their own specialty or a mission space where they pride themselves. They have a vision, and they march on towards solving a lot of energy-related challenges for not just United States, but just the entire humanity, just the entire globe. So we are a vital source for the nation's energy and security future. Our mission, as it's written on the right side of the screen, is we discover, demonstrate, and secure innovative nuclear energy solutions, clean energy options, and critical energy. So these are kind of the three driving pillars that we work really, really hard and try to develop and take this technology forward. What is our vision? Our vision is to change the world's energy future and secure our critical infrastructure. And how do we do this? We cherish a lot our INL values, which is excellence, integrity, ownership, teamwork, and safety. So all 5,000 odd INL employees work really hard to maintain these values day in, day out, to enable our mission space and march towards our vision. The pictures here shown are from very different technologies. One of the ones that on your left, the second picture is sort of a set of transmission lines that you can see that help us carry power from remote generation locations to our neighborhoods, and so on and so forth. So there's all kinds of technologies that we work on, including batteries, human factors, biofuels, which is kind of shown as pellets down there in the third picture. So this is kind of what we are all about. We're all about nuclear energy. We're all about clean energy solutions and critical infrastructure. Before getting into the details of what a microgrid is and what are we going to look at as far as understanding microgrids, designing them, and even deploying them, there is a very systematic approach that is needed for making microgrids work. But before getting into that, I wanted to make sure we set the stage right on what do these electrical terms really mean. And I've purposefully picked only one of them. The term that is picked here is called power rating. A power rating is typically a term used for understanding how much power, or how much, in layman's terms as well, how much current is at a given voltage a device going to utilize for its normal functioning. So here I've thrown a few devices or a few technologies that we use and we are aware of. A hair dryer, a pretty solid hair dryer of a significant size, typically used in residence, uses about 1.5 kilowatt. And this is, again, just an example, or just to give you an idea of how things look like. That could also mean there could be a hair dryer that is smaller than this, and there is no fixed rule. It's just a ballpark number to give you an idea of what I'm talking about here. Another good example that we use in our daily lives is a dryer in our home or a water heater. Now that has a little bit of a variation. It could vary anywhere from 3 to about 20-ish kilowatts, depending on how large your home is, how large of a dryer you use, if it's a dryer meant for larger carpets and things like that, or it's a normal clothes dryer. So depending on that, the larger the size, the more power it is going to draw, so the more amperes it's going to draw. And then it is necessarily going to amount to a larger amount of energy that you will be consuming for doing the function. Moving from residential to commercial side, so imagine a small office building like a dentist's office or a small restaurant, so that is sort of a commercial entity. Utilities like to deal with residential and commercial entities in a different way. Their contracts are different, their service mechanisms are different, and so on and so forth. So they could be anywhere from 50 kilowatt to about 350, 400-ish kilowatts. So what are the type of loads that a small office building or buildings are going to have? We definitely have lighting, they'll have HVAC, they'll have water heating, definitely water sprinklers to maintain, the area around it, and obviously whatever product or service that they do. If it's a dentist's office, of course, they're going to consume a lot of energy to run their machinery. So all of this put together is going to be a pretty decent chunk. Typically, shopping malls come under commercial type connections as well. So if it's a huge shopping mall, then definitely it's going to take, 350 kilowatts or even more than that. So it's hard to say how much exactly it is, but when we build and commission a particular facility, at that time we get a pretty good sense of what it is as far as consumption wise, and then what kind of contract it needs, so the utility provides a particular level of service to that particular customer. So that's kind of the ballpark of what we're talking about. And then the third and the final one, yes.
Oh, I was just going to ask, are these, now the hair dryer, I can understand that it's just a single usage, you're drying your hair or drying a load of clothes. For the commercial, the small office building and the high rise, is that over a year? Is that just a snapshot of a moment in time? How do you, over time, how do you measure these values?
That's a really good question. So we're talking about instantaneous value here. We're not talking about what happens over a day or an hour or a year. Now, what happens is when you have a particular, so let's just take a small office building, right? So if the office building is rated at 350 kilowatts and it operates at full capacity for an entire hour, which means the energy consumed by that office building is 350 kilowatt hours. So that's the energy content of that particular 1 hour. Kilowatt hour is also commonly known as, just unit in very common terms. And you say, hey, how many units did you consume? How many units of energy did you consume? So in that case, it's either 1 unit or 2 units or 10 units or whatever it is. So that is basically kilowatt hours. Is a very standardized measurement that we use. And I really like that question. That's a very important question because we need to understand not just instantaneous requirements, but also what is our daily energy requirement, what is our weekly energy requirement, and then so on and so forth, because that is how we build energy systems. We need to plan accordingly for actually the worst case scenarios. So how do we look at that? I'll get a little bit into how do we look into those design parameters, if you will, during the planning stages. Does that help answer the question?
Yeah, it does. Thank you.
Perfect. And if we happen to visit a larger city, actually Idaho Falls probably is a little bit smaller to the scale that I'm referring to here, but more like a Salt Lake City or a Denver or a Seattle, where we see very large high-rise office buildings, 30 floors, 40 floors, 50 floors, that sort of those sort of buildings, where there is a significant load of lighting, computers, HVAC, elevators, and so on and so forth. So everything needed for a building to function. Some of the buildings could go as much as or even exceed 1 megawatt, which is a pretty significant load. So that is kind of the sense of the scale that we're talking about. Now, why did we want to look at this? we wanted to look at this because microgrids are so flexible that they can be applicable to most of the things we're talking about. And I'll get into how. There is a certain aspect of change that our power and energy systems or the electric grids in general are facing, right? One of them is the adoption of renewable energy sources, then introduction of electric vehicles, and obviously now microgrids that have started to come up in this particular gamut, you know. So in this particular sense, the electric grids traditionally have had only a unidirectional flow of power. What I mean by unidirectional flow of power is we had centralized generation stations, which were typically away from communities. We had transmission, which essentially picked up the energy that was created in generation stations and transferred it to our communities. And then there was a distribution network that took this energy from transmission and delivered it to homes, i.e. residential customers, commercial customers, and industrial customers. So now what happened was we decided to introduce significant fraction of renewable energy sources in the form of large wind turbines and large solar panels. If you happen to drive by in Wyoming, you should be able to see throughout the wind farm, throughout the agricultural farms, large wind turbines. So what happens is the power output from these large wind turbines is combined, and then it is connected to transmission lines. There is a significant increase in wind power installations in Idaho as well, as we are probably all aware that Idaho has quite a bit of windy days.
So it sure does.
And we are actually quite fortunate to have a lot of sunlight as well. So we definitely will be seeing residential as well as commercial solar installations. So what happens is there is obviously a little bit of variability associated with renewable energy. So sometimes it peaks, sometimes it dies down. So the grid has to be able to figure out how to deal with this situation. The second application or the second change that the electric grid is seeing is electrified transportation. So far we've used conventional fuels, gasoline, diesel, to run our vehicle systems. So we call them conventional vehicles, right? So they rely on conventional fuels. There is a distinct advantage of going towards electric vehicles, which is their overall efficiency tends to be higher than conventional vehicles. Now, what it means is we need to have batteries on top of vehicles. And some of you might have heard the previous talk that Kristen mentioned, which was given by Lee, that how do batteries help navigate transportation now? So electric vehicles obviously can charge from either the centralized electric grid, or you can create standalone supply for electric vehicles as well. So there are several ways you can try to make this work. Now, and the third parameter is, or the third major trend is microgrids. So we'll get into what are microgrids and how it leads to different things. Now, the tricky part with a lot of these newer trends is it leads to power going in the opposite direction than what the grid was built to do. Now, why is this very, very important? Why is a two-way power flow tricky to deal with? To give you a context of what the electric grid is in the United States, is it is termed as actually the largest man-made machine ever built. Let me repeat it. The US electric grid is actually the largest man-made machine ever built. It essentially stretches from the East Coast, from the Atlantic Ocean up to the Pacific Coast. It actually stretches from some parts of southern Canada up to northern parts of Mexico, some parts of northern Mexico, and it covers the entire United States. If you look at only transmission, and transmission begins at 230 kilovolts and above, we have in the United States over 120,000 miles of just transmission lines. I'm not even getting into distribution lines because that's another several tens of thousands of miles. So just the transmission line network in this country is over 120,000 miles. So all these systems, that the pictures that you see here, as well as coal-fired power plants, nuclear power plants, hydropower plants, wind, solar, all these connections happen to the same electric grid. And guess what? Our homes are connected to the same. Our dentist offices and malls are connected to the same. And also the industrial customers are also connected to the same electric grid. So if there is anything that goes wrong with one part of the grid, it does affect its at least neighboring parts of the grid. And there is a huge engineering field within power systems that deals with how to deal with such situations. For managing this particular electric grid, we need a lot of control systems. By control systems, I am referring to a gamut of devices, an array of devices that also has measurement and sensing, that also has controllers that decide when to switch on and off certain devices, and how to, in general, operate the system. It's a very dynamic system. For all the math geeks out there on this webinar, it's a very, very nonlinear system, an extremely nonlinear system. And if you're familiar with what that means, is it is very hard to model every little detail of this system and understand it. So you have to be very, very creative in how you model part of it versus all of it. And it also depends on what you're trying to study. So now in all of this large electric machine, there was an introduction of what we call microgrids. Now, why is it called microgrids? As you can probably imagine, the size of the US electric grid, as I just mentioned, we typically refer to it as macrogrids or bulk interconnections. And the US bulk interconnections has three areas. One is Eastern, second is Western, and third is Texas interconnection. As the name suggests, Texas interconnection is essentially almost the entire state of Texas. The Eastern interconnection is anywhere from the East Coast up to the Central Plains in the US. And the Western interconnection starts from the Rockies up to the Pacific Coast. So these are bulk or macrogrids. Now, what we are referring to here in microgrids is a very specific methodology. It's a very specific terminology of having the ability to local electricity generation, and it might include storage. It has the ability to connect with the main grid, or it can isolate itself from the main bulk electric grid or the macro grid and still function either at a complete level of operation, so maintain complete functionality, supplying all the loads, or a partial functionality. But it has also the ability to reconnect to the electric grid as and when needed. So now one might wonder, why do we really need to do this? Well, since this is a ginormous machinery that works day in, day out in real time, and that's very, very important. Why is this a real-time phenomena? The real-time nature comes in because we adopted in this, globally it has been adopted, an AC or alternating current microgrid. So when you generate X amount, you have to be able to consume that same amount of electricity. There are some very minor, by minor I mean scale-wise, given the size of the bulk electric grid, ways to store energy, which includes batteries. It includes what we call pumped storage hydro. and there could be a third option of chemical or thermal storage. But as compared to the main size of the electric grid, these still are relatively small in size. Now, why do we need to disconnect from the electric grid, right? Imagine this. We've had a couple of events in Idaho Falls, as in one of the transmission line that feeds in to the Idaho Falls city area has a fault. Fault could happen because of strong winds, excessive rainfall, excessive snow conditions, you name it. Because it's a structure and it could sometimes break. What happens in these cases is there is another important facet in the electric grid, which is called protection systems. These protection systems will kick in and isolate that fault or isolate the troubled part of the grid. Now, what happens is that hampers the supply to the customers in Idaho Falls then. Now, how do we manage this? So if such a condition occurs, then how do we run our hospitals or government systems or any other essential buildings that we want to, right? So if such a situation occurs, then you can resort to ways to this methodology of microgrids. It helps us tap into local energy. It helps us enhance resiliency. And it in general helps us keep the lights on when our main utility grid is having challenges. Most of the challenges are going to be because of natural calamities, but there is also a possibility of cyber threats as well. So that could paralyze parts of the grids. So in general, this is kind of the need why a lot of communities that are remotely located, military bases, other critical facilities, and very, very specialized operations, like data centers, for example, right? A tech industry data center is an extremely important part of their operation. So they could use local resources, including batteries and fuel cells and things like that, to make sure their data centers are up and running. So that is one place where you could use, one application where you could use microgrids to make sure that your critical functions are still up and running. But that does not really mean that all your functions will always be operational. It could only mean a partial state of operation, but it certainly helps. So that kind of gives the background on what are microgrids, where do they fit, and how do they help us run our electricity grids.
Manish, maybe we could take just a moment and just invite our participants. Does anybody have a question about what Manish was talking about, or clarification, something that you didn't quite understand before we go into this more real world examples? Wait just half a second here.
Sure.
You explained it very thoroughly and well, so we probably won't have any questions.
I'm glad, but I'm happy to answer questions anytime.
Well, let's go on, and if folks happen to think of a question, please feel free to put it in the question bar. So go ahead, please.
Sure. Perfect, thank you. So now that we have gotten to know a little bit about microgrids and what they are and what they can be used for, there is a very rigorous process that includes modeling, understanding why you are doing microgrids. Is that even a good fit? Which in engineering terms, it's called feasibility analysis. So there is definitely a big emphasis on what we are looking for. What are the objectives of having a microgrid? What can we really invest in? At times, another engineering phrase is saying, I'm going to make a system that is gold-plated, which means there is no constraint of expenditure for a particular system. In that case, you can definitely try to build a gold-plated electric grid or a microgrid. In that case, it's going to be extremely expensive, but it will try and suffice most of the functions that you're looking for. So from that context, there is a lot of planning that needs to go. Additionally, there is a lot of engineering work that goes in as well. After the planning work, you have to look into what are the things that may or may not work given the local conditions, right? Is a solar panel feasible for the given location or not? It really needs to be understood from that feasibility study. If it is, what is the potential? Can it cover 10% of your load? Can it try and help cover 50% of the load, and so on and so forth? So there are a lot of trade-offs that are based on technology as well as the finances associated with these technologies. So what you're seeing here is a picture, and it's kind of I don't want to use the word 360-degree picture, but it's like a wide view picture of the highway that we have at the lab, and this is one of the city offices that I was referring to. And I work, I don't know if you can see my screen, I kind of work in this little tiny corner in the right side, where there is a bunch of those simulators and devices that are quite sophisticated actually, that help us understand and design things like microgrids. Now, why are we located here in the mix? You can see a bunch of other things. You know, there is 3 electric vehicles here. There is some hydrogen technology in the middle, and there is a couple of other expansion plants on the bottom right side, where there will be thermal loads and thermal loops connected, being built out. And in the right top, right here, is our own version of what a test microgrid looks like. So what we do here in the space that I'm engaged in is we try and knit all these different players together. And in addition to these things, right outside of the wall on the right side that you see here near my cursor, we have some solar PV outside, and it's rated about 30 kilowatts. There is also a mobile or flexible solar that's about 5 kilowatts that can be loaded and can be driven to different sites for demonstrations. There's a gas generator and a flow battery energy storage, which is a relatively newer energy storage battery of about 335 kilowatts, and a small home, essentially. What it is a large trailer that is kind of modified with all typical residential loads that you would see. So that's like a smart home appliances lab, if you will. So what we can do is, using the digital real-time simulation capability that we have, we can connect to any of these devices and technologies, right? And in the real-time simulation, what we do is we create something that we call a digital blueprint. And I'll get into a little bit of what that means. But essentially, when we use a device, say, for example, we have an electric vehicle that we connect to the simulators back there, it is called hardware in the loop. So as the name suggests, we actually use a device that is connected to a simulator, where the simulator is simulating real world conditions, and through that digital blueprint, and we can understand the behavior of that particular device. So it could be an electric vehicle, it could be hydrogen technologies, it could be thermal technologies, it could be other microgrids, it could be other solar devices, and so on and so forth. And when it comes to controllers and protection systems and things of those nature, we do them right next to the simulators itself. Now, one might wonder, why do you need this? What happens is, as I said, there is a lot of uncertainty in how different technologies will interact with each other. Sometimes batteries provide the right function under certain conditions that the grid needs, and at times it may not. And the reason for that would be the control function associated with a particular technology may or may not allow that. So, for example, if you're looking for a voltage support type service from an energy storage device, does the converter built on top of that battery have that functionality or not? And if it does, how do we verify it? Because when you model things, the model is going to be as good as your information underlying that model. So that's why when it comes to newer technologies, this is a very important way of doing things where you actually use a hardware device and you connect it to the simulator. Now, what is the specialty of the simulator? As the name suggests, it is real time. So when you look at your laptop or your desktop, you could do a simulation of say 5 seconds. That 5-second simulation in a what we term as non-real-time environment may not necessarily be 5 seconds in real-world clock. But the high-fidelity simulators that we have and the way they're set up, they will allow you to do simulation at that real clock speed. So that is why we can connect devices such as the electric vehicle or a solar panel to it. Why we need this is, say you have a particular area that you want to study and you want to connect a bunch of electric vehicles there. The problem is you probably are not going to be able to have an access to several tens of miles of actual distribution or transmission lines to do an experimentation, because they 24/7, 365, they have a single function, which is to provide electricity to customers. So in that case, things that cannot be, it's not feasible to have access to, those things can be modeled in those real-time simulators, to which we can connect devices such as those shown here, or technologies that are shown here, in order to understand how they can interact with the rest of the electric grid. So if you have a large number of electric vehicles connecting to a particular feeder system in the distribution network, what is the impact going to look like if they all start charging at the same time, or if they all of a sudden change from charging at a low power level to a high power level? Does the electric grid have the necessary means to provide that? So it kind of helps us understand and answer these what if questions. Now, getting into some of the real world examples that we've done in this particular space. About 3 years ago, we completed a project now, which was funded by the California Energy Commission for a site in Northern California called Blue Lake Rancheria. The Blue Lake Rancheria is a very interesting site, and I have personally been there several times as a part of this particular project. It's a first of a kind microgrid that can separate or isolate from the main electric grid or the bulk electric grid seamlessly. By that I mean it can instantaneously switch to a local mode of operation or instantaneously reconnect without letting the lights really go out. It's kind of a big deal because this site is pretty huge, and I'll get into how big the site is and everything. The location of Blue Lake Rancheria is quite interesting. It is located in a very remote location up in Humboldt County. To those of you who are familiar with California geography, it's about 5 hours or so north of Sacramento. So you keep driving north through the Shasta Mountains and everything. It's a very remote location. Even getting there by road is quite difficult. So as you can imagine, if getting by road to that particular location is difficult, then obviously providing electricity transmission is also going to be difficult through the mountains, and maintaining it and obviously providing a reliable supply is tricky as well. So this particular site, that is the Blue Lake Rancheria, is an excellent location because the community there is a very progressive Native American tribe community. Their charter involved becoming energy sovereign. So they wanted to have ability to make sure they can provide at least some level of resilience when things are not right. As everybody is probably familiar, California faces a lot of wildfires, a lot of water shortage as well. And their area up there is also prone to earthquakes. So there are significant challenges posed by Mother Nature there to just the general access to electricity. So having considered that, this progressive tribe decided to pursue novel technologies such as the microgrid, solar PV, energy storage, to help them gain some of that energy sovereignty. So we worked with the local university there, Humboldt State University, who led the project as well, the local utility, Pacific Gas and Electric Company, who I cannot emphasize enough was very, very supportive of this project, and they showed it through their continuous support throughout the 3-year project. Siemens was essentially the provider for the microgrid energy management system, and Tesla provided their energy storage technology for this particular project. Now, why is the microgrid energy management system very important here? The microgrid energy management system here kind of sits at the top of the operation of this particular facility. So this facility had a hotel. It had a large hall, a function hall, if you will, and they had a large casino. And they also had a gas station and emergency communication center as well. So you can imagine for a remote location like this particular site was serving an extremely important role. For the tribe's operation, their priority of making sure the casino works under most conditions was also important, because that is associated with the revenue of the tribe over there. So as you can imagine, this is a pretty important facility. Now we had an access to their facilities managers and their staff, and obviously Pacific Gas and Electric, to figure out what constitutes this site, and how do we figure out a way to work with this particular location and figure out the best microgrid that we can design and deploy. Because just doing a feasibility analysis and designing something is one aspect, but when you try to roll it out and deploy in the field and make it work is a whole another ballgame. So we worked with all these players involved in this particular project, and what we did at the lab that I just showed in the previous slide right here was we got the Siemens microgrid controller deployed here in the location. Kristen, are the audience able to see my mouse or no?
Oh, yes, it's very clear. Mm-hmm.
Okay, perfect.
Yeah.
So the controller, the microgrid controller, and a bunch of other devices that help us connect and disconnect from the Pacific Gas and Electric grid were all connected here in this particular part of the lab. We had PV connected outside behind this particular wall, and some of the converters were placed kind of here for the PV that I just mentioned. And we connected a bunch of loads and created a digital blueprint of this particular site. And then what we were able to do was do all kinds of what if scenarios that we wouldn't be able to do without affecting the actual operations of the site. So the only better way of testing this was to actually taking a device and deploying it in the field. So this testing or this approach helps us take it to almost the level where we can deploy it in the field. So we tested all kinds of scenarios when we lose the main electric grid, or we lose one of the diesel generators that the site had, or if we lose the PV panels that the site has connected, or if the battery was having a low state of charge. How do we plan out and figure out a way to still function under a tricky situation, which is not a blue sky operation. So we did all kinds of things like blue sky, gray sky, and dark sky operations. So which helps us understand how these systems can be designed in a better way. And then all of this feedback was being given in again, ironically real time to all the players involved in this. And what we were able to do was we were able to transition from a site that was completely reliant on what they had as far as the supply from Pacific Gas and Electric, and a very marginally low ability of when the PG&E grid goes out, being able to function with some of their critical loads like servers and things like that, to a place where they were able to maintain supply to their site to a very significantly high value. So one of the articles that we got to know after about 2.5 years was this particular thing that is mentioned here. The site was able to actually provide shelter and power supply to about 10,000 people, which is about 10% of their population during the wildfire prevention measures that PG&E had to take when they had to shut down part of the electric grid. So which we considered as a really remarkable estimate to what the team was able to accomplish. That we were able to show and demonstrate that part of this technology really works, and it is there to help all of us when things aren't right. So it was kind of one of the highlights that we all considered that we're very, very proud of.
Manish, could I think I read an article about this, either in the Atlantic or New York Times or someplace. And this was and I'm sorry, I've forgotten the name, but this was that huge fire that just kind of came up out of nowhere, and PG&E, this was what, 2 years ago, 3 years ago, and PG&E had to immediately start cutting off power. And we all saw the pictures of people driving down the roads to some sort of safety with the flames on every side. But what this tribe was able to do was they were, if I remember correctly, and please correct me if I'm wrong, they were able to keep their medical clinic going, their convenience store, their gas station, the casino, their government operations, and it served not only the 10% of the population in that area, but it was also a key area for the firefighters because they had guaranteed power there, and they used it as a, I forget now what it's called, but like a command center, because they had that kind of consistent energy source. I mean, it was a remarkable story. So I'm sorry to interrupt you, but it just it really was incredible what this, how this served this remote community in a terrible, terrible time.
I think you summed up the article better than I could have. So no, absolutely, and that is one of the things that I'm very proud of, how we were able to help this particular tribe to achieve one of their energy goals at least, and they were very keen on actually utilizing as much as possible their local PV generation as well. So they wanted a specific mode of operation where they maximized the utilization of PV. So they wanted to reduce their imports, and they didn't want to use so much of their diesel generators and things like that. So we were able to go through all these what-if scenarios and make sure that the very clear objective that the tribe had about their energy goals was met. So obviously it needs a lot of clarity from what we are looking for from a microgrid. Next, this is an ongoing project right now, and it's an equally exciting project up in Cordova, Alaska, and some of my colleagues are engaged in the day-to-day activities. I'm quite informed about this particular project. It's interesting case because in Alaska there is no transmission network, so there is no huge transmission lines that carries power from large generating stations to communities. So essentially what they have is a lot of microgrids. All these tiny communities and remote communities have their own generation. It just puts power on their distribution grids and they utilize it locally. So essentially it serves as a very interesting place for us to do a lot of innovation, because usually in the continental United States, it's very difficult to get a site that is not connected to the bulk power system at all. So this one serves as a test bed for us to do a lot of innovation. What we did here was we adopted some new sensing mechanisms that do things at microseconds level, that senses the conditions of the electric grid, gets that information, ships it to a central command center, if you will, where decisions can be made in an automated fashion to enable the operation of the microgrid. In this case, there are several new things that the team has looked at, and there is a couple of other national laboratories, Pacific Northwest National Lab and Sandia National Lab, and a host of other university and local partners that we have, the city of Cordova, and so on and so forth. So in general, all these people engaged in this project are looking at very advanced functionalities that can help us manage the operation under extreme conditions, because in Cordova there are challenges. There are very severe challenges actually that are posed from the environment, which could involve avalanches, extreme snowfall. At times there is a lot of rainfall, and since most of the distribution grid can easily get affected by such harsh conditions, it's hard to maintain reliable power supply for 365 24/7. So how do we disable parts of the grid, remove the faulty part, and still make sure the businesses are open, the community centers are open, the hospital is open, and so on and so forth. And here, hydropower is playing a significant role, as shown in the picture down there, because they have a pretty good source of hydropower and a pretty good head because of the mountainous region, as well as the snowfall, as well as partly the rainfall that we have.
Manish,
so was there a question?
Yes, there is.
Okay.
So I'll just read it. I can't summarize it. During island mode, how many hours is the BESS design to support the microgrid? Also, how much on-site diesel fuel storage was included to support the microgrid to support an extended outage?
Okay, I believe the question is more relevant to the previous example that I just discussed.
Yeah.
So that's a very, very good question, and that's a very valid question. If my memory serves me correctly, the diesel generator on site was rated at 1 megawatt. And at any given time, they were able to hold over a week's supply if the diesel generator was operating at full power. On an average, I believe the load was somewhere between 700 and 800 kilowatts. So the generator was a little bit oversized as compared to the entire load. But the peak loads could go higher, and obviously, if they had facility expansion plans, then that changes a lot of things there. So given that significant source of power, the battery energy storage, I believe, was rated at 420 kilowatt hours, I believe, or 450 kilowatt hours, one of the numbers. Anyhow, so with that battery storage, the power rating on that battery storage was about 400 kilowatts as well. So that could suffice about part of the day if it was completely on BESS or the battery energy storage system. It could suffice for a pretty good chunk of the day. So the usual, now there comes in the picture of what can you realistically do given a site, right? So we couldn't allow any power back onto the electric grid that was more than the PV generation, because in California, you can only put power back on the grid. In other words, you can export power to the electric grid only if it is made from PV or wind and so on and so forth. So renewable energy sources, essentially, as they have defined it. So for demand response type things, since it's a technical question, and I believe some folks might be aware of this, for those type of scenarios, the battery could help manage the site quite well. With the PV and the battery, it was few hours could be easily managed. Now, if it was days together, then at some point of time we had to go to the diesel as well, because when we talk about days type of islanded operation, then the diesel is the solution to go to, because the PV will generate based on whatever solar insulation we have, and the battery will keep charging. But if you on the other hand, drain it to keep up the loads during the day, then during the night times, it's going to be very tricky because there is not going to be any solar. And once the battery discharges, then there isn't much left in the tank. So you have to switch to the diesel dominant operation as well. So I hope that kind of answers the question.
Yeah, thank you very much, Greg. That was a great question. We have another question from Alan, and this is for the California project too, Manish. I noticed the diesel generator for the California project. If the utility feed disconnects, are only a subset of loads seamlessly transferred while other loads are initially shed and are later gradually restored. I can understand quick ramp up of battery PV inverters, but I'm not sure how fast a diesel generator can react in an event.
Right, so there were several scenarios, and this is a very good question again as well. There were several scenarios to deal with, and it can be broadly classified into unintentional and intentional islanding. So an unintentional islanding is obviously when there is a fault on the upstream of the electric grid, and you do not have enough time to react, and the switches automatically operate and you're isolated, right? In that case, there's a different way of dealing with things, because if your load is high enough, or if the load is significantly larger than what the battery power rating is, then some of them will have to be shed. Then there won't be a complete seamless switch. On the other hand, if you're doing an intentional islanding, then what you can do is the microgrid manager or management system will figure out a way to charge the battery as much as possible. And it has a load forecaster that goes on in the background that tries and understands and learns from itself essentially and its surrounding, that how much load do I typically carry. So if I'm at noon and I have a pretty good confidence, that at 1 p.m. I typically have so and so load. So it will try and manage to do an intentional island in that sense. So in that case, you probably won't have to shed load. Now, as I said, they luckily had a very big diesel generator on site, which was deployed as some other activity that they had in the past. In that case, if you wanted to do a diesel only operation, then obviously there was a way you could do it. The only problem is one of the interconnection requirements is you cannot parallelize a 1 megawatt generator with the electric grid. And that's a safety issue, because what happens is if there is a line maintenance job or some other maintenance activity that is going on upstream, and the 1 megawatt generator kicks in and starts putting power back into the grid, that could lead to fatal challenges. And it's a safety hazard then, because the utility will not know the behavior of your 1 megawatt. So you could not parallelly run the 1 megawatt generator with the electric grid. So there's a lot of decision variables and factors that come into picture when you try to run this.
Great, thank you very much. And we have another question. This is from Jacob.
Sure.
This is from Jacob. Okay. There is a blueprint for Blaine County. Some have suggested that microgrids could provide the backup necessary during an outage. What type of fuel source would you recommend to provide enough power to match what the proposed Idaho Power Redundant would supply?
That is, again, an excellent question. And it is going to be hard to say whether it makes sense to do one fuel type or different fuel types. If you take the example of the Blue Lake Rancheria that we just talked about, one of their primary sources, obviously, for long-term resiliency was diesel. The other environmental friendly source, if you will, that the county wanted, or the facility wanted to use, was solar. They even tried biomass and fuel cell power system, which is essentially hydrogen power as well. These have very, very different characteristics. Solar, obviously, we all know it's intermittent and variable at times. It might not be there, so you need battery storage with that. As I said, when they did the days they needed the days time scale resiliency, then they chose to do a diesel. So definitely there are a lot of microgrids that have used that. So that could be a perhaps a suitable candidate. Does that mean, so again, we have to understand one thing that I apologize that I missed. When we undertake an activity like this with microgrids and things like that, for this particular example, the Blue Lake Rancheria was responsible for the operation and maintenance of everything that goes on that site. So it involves the battery, it involves the PV, it involves the diesel, maintaining the supplies, and so on and so forth, and also the general electric maintenance that they have to do. Now, there are ways to deal with it. You could get a company that helps you with operations and maintenance. There are several ways to deal with that, but essentially that becomes the responsibility of the site itself. So having said that, you have to also consider the local factors on what is it as far as fuels that you can maintain at your local site. What is accessible to you given your location? In some places, it makes sense to get natural gas generators. In others, it makes sense to get diesel generators. Others, it would make sense to just get PV. So if you're located in something like Nevada or something, then PV is pretty strong. Getting a pretty solid battery backup could also help your case. But again, the characteristic of the source and your need has to match.
Thank you. We have a quick question.
Sure.
It comes from Paul. He asks, if we became our own microgrid, would all the existing solar, rooftop and ground-based, be able to be utilized by that microgrid?
Can you please repeat that question? I'm
sure.
A little bit.
Yeah. So yeah. If we in our valley developed a microgrid system, all the existing solar that we have, because we have some freestanding, some mounted on rooftops, would those solar systems be able to be utilized as part of the photovoltaic array that the microgrid would tap into?
Again, my answer is not going to be based on any detailed study. I'm just making a best guess.
Okay, that's fine.
Based on the question that I have. There are ways to leverage PV, residential PV. The biggest challenge that comes into picture is the point that I made earlier, which was the electric grid is very tricky because there isn't really a grid scale storage, like a bulk grid storage, available as on now. So having a suitable energy storage is going to be extremely important. Mm-hmm. Secondly, you have to have a very good visibility in what each of those panels are doing. So there is a lot of communication that will be required and a very sophisticated control that will be able to use this PV. Now, one topic which obviously could go on for hours that I did not introduce here is what happens when things change in the electric grid, and they change every second. It is called power system stability and controls. So basically, as we switch lights, as we switch water heaters, as we switch large loads like furnaces or induction machines and things like that, there's a lot of dynamics that is associated with it. So in a microgrid, you have to be able to maintain a certain level of what is in physics world or in electrical engineering world called inertia in the system. So that there's a certain level of stiffness in the grid. So the grid stays at 60 hertz plus minus delta, and the voltage levels at every customer stays 110 volts plus minus delta, or 220 volts if it's 220 volt customer, or 3.3 kilovolts if it's a commercial load, and so on and so forth. So anyhow, So maintaining these parameters in a very tight band is important. So we need controls, and we need essentially some sort of an inertia that helps us manage at least these large deviations in the grid. So one good example is if you have a microgrid and suddenly your PV goes out due to a fault. It's just a short circuit fault and it goes out. So you suddenly lose, say, 400 kilowatts of PV. What that is going to do is the frequency of the microgrid will dip significantly. So your other generators have to be able to kick in within finite time to power the grid back up. Otherwise, due to the frequency dip, a lot of other things will start shedding. And that kind of compounds fairly quickly in a microgrid because it's a very small a small machine, and by that I mean as compared to the bulk electric grid, it's a really small system, if you will. A small community, a small town. Even Idaho Falls is very small as compared to the national electric grid. National electric grid is huge, so there is a lot of machines that will help us respond to deal with sudden changes in the grid. So can one do it? Perhaps yes, but there has to be a lot of other things that have to be studied and other technologies that have to be leveraged to make it work.
Thank you very much. We've had such excellent questions that we've only got a little less than 15 minutes to go because the system that we're on is scheduled to stop at 7. And
okay.
So I know that's been a great talk. So what would you like to highlight?
You know what? I'm gonna go to my. I'm gonna do a quick rundown in things, within like a minute, and then go to my final slide. How about that?
Sounds good.
Okay. So one important thing that we talked several times now is, what are these critical loads and how can you use microgrids, right? So one of the best things that you can achieve using a microgrid is you can take care of your critical loads. And that goes back to the question that was posed earlier, was how much time can I keep things up? That really depends on how long do you think the supply from the main electric grid is not going to be available, right? So if you a good example is if it's if you're familiar with the calamities that happen in southeast, i.e. Florida, sometimes it's days together when there is a large hurricane or something like that literally wipes out the entire road system, the entire electric grid, and so on and so forth. So it's going to take a few weeks, if not months, to get back on track. We all know the example of Puerto Rico, where almost a significant chunk of their electric supply system was affected. So in this case, it's going to take weeks, if not months, to get things back on track. So the best thing we can do is hopefully we have enough resiliency built up in our system that our critical loads like hospitals and emergency communication centers and things like that stay up. The next thing you can do is you can try and maximize existing resources, right? So if you have a pretty good wind portfolio, or if you have a pretty good solar portfolio, you can use a lot of existing resources that you have to figure out a way to use them. Obviously, it involves investments in technology. It means investment in controls, communications, and so on and so forth. But definitely, you can try and utilize what is local to you. And the third really good example is if you're planning to add anything new to your electric grid, say you're thinking of adding batteries, or say you're thinking of adding diesel generators or electric vehicles for that matter of sake, how can you realistically do grid rearrangement? And that's not a very trivial topic to say. Grid reconfiguration to figure out a way to keep power on at your critical facilities, at different tiers of loads that you might identify as not very critical but very, very important, and so on and so forth. So you can really look at future grid expansion in a very different context. And then I want to kind of wrap up the summary and some of your questions have been really, really insightful. I definitely appreciated them. So I want to leave some final thoughts with everybody. I think microgrids are a really different way and a novel way of managing local electric loads and local resources. And definitely that helps us get through some difficult times, especially when it's a natural calamity or, unavailability of utility supplies due to cyber events and things like that. They add a tremendous value to our communities and neighborhoods, if you're able to optimally utilize. And this is quite evident from the Blue Lake Rancheria example that I gave, where the tribe was able to use their facility to provide shelter to literally thousands. And it's such a nice example where the tribe was so much tightly coupled with their community, and they share the challenges that their community is facing. And it's such a nice example, right? And again, I harped enough on critical loads. We can definitely keep some of them up. Depends how long is a really good design question, and obviously an economic consideration to have. We definitely add resilience and reliability to our electric grid, right? Because there is parts of the grid that definitely need more modernization, if you will, and others not so much. So how do we figure out a way to make sure our grid works and our electricity needs are met under blue sky as well as dark sky operation? And finally, at INL, we're really interested in this particular space of research and development. We've had local, regional, and even a national level impact in this space. And it's again, I'm saying this as INL, but the true credit belongs to all the different teams that we've been fortunate to be a part of. It was all entirely a team effort. But from this context, I'm speaking for INL. INL's interest in this space has been really solid. Like we've really appreciated the teams and the opportunities to work in this particular space. And finally, I guess if you'd like to know more about INL, there's a lot of exciting things we do. Feel free to check out one of the social networking pages. It has some really cool information. I believe it's Facebook, Twitter, and I don't know what the third one is. And the fourth one is LinkedIn, definitely. And if, as Kristen mentioned, her friend happened to have an INL tour, feel free to contact tours@inl.gov. And I think I probably have about 10 more minutes left before this thing will cut off. So I'll take a pause and wait for comments, questions, any discussion you would like to have.
Sure. Let's see if anybody posts a question. I have maybe a short question. I was intrigued by the question about integrating home rooftop solar panels into a microgrid, because a number of people have solar panels here. And I mean, if we thought that we could contribute to the greater good, this is a very caring and compassionate community. I think people might be interested in stepping up to that if it worked. But you said that it would take a more specialized control panel or system. I'm not sure the right term. How far out would the development of that kind of a control system be? I mean, would it be a couple years out, 5 years out, 10 years out? I was just kind of curious.
Yeah, sure. No, that's a good question. It's hard to say where the technology is in a fixed time as far as when it will be solved. But I can definitely say this. There are, so with things like solar panels, right? We're trying to understand and conceptualize and develop. And this, by we, I mean the entire community, the technical community that is involved, in figuring out how to use these technologies so that we can still carry on the functions that we used to be able to in a conventional context for the electric grids, right? So the way this system was, so imagine this, right? You're driving down a highway, you feel like you need to get a cup of coffee or get a soda or whatever, right? You take an exit, right? The exits in the United States are typically unidirectional. You typically have an exit on the right. There are some exceptions. Then you turn around and then you get onto a smaller road, if you will, and then drive down to a gas station, right? And get a soda or coffee or whatever. That's how complex this whole system is. So everything that was built in the system was only looking from generation to transmission to distribution. So if you can imagine this millions and millions of devices in the system that are only designed and built to look in directionality was not even a thought in a way. You know, it's like we're only looking from power flowing from A to B, never from B to A. So figuring out all the protection systems, the visibility and observability, the controls that will allow us to do this is going to take some time, unfortunately. Since a lot of your audience is kind of very well informed on this, which is kind of exciting for me to know, is innovation in energy is a little bit slower than some of the other things that we might see. Healthcare is a good example. Right? Healthcare innovation takes a long time as well. So it's going to take time, but I think it is going to be possible someday.
So we have a late quick question, and honest, you only have got a couple minutes to answer this.
Okay.
Dick asks, since INL studied the power demand in Hailey and Ketchum, how much power would need to be generated in the city of Hailey to provide backup power for emergencies during a blackout?
Wow.
It's a county commissioner asking you that, so.
Dick, it's a loaded question. I have to apologize. I don't know the number on top of my mind to give you the exact answer. I have to apologize for that.
Okay.
Essentially, if I have to give a theoretical answer, the answer is whatever is the load demand in Ketchum and the losses that you would incur in exporting power from source to the load. So once you start putting power on any wire, there is going to be some losses. So essentially the losses plus the entire load that you would expect at Ketchum, I guess. So.
Great, and we heard a thank you for your answer on that.
Thank you.
So I think we're going to have to draw this wonderful talk, very informative talk, to a close. There is one more question, but we'll invite you to submit that question. We'll look at it afterwards, and Manish will respond to your question, Alan. And so also, if anyone has suggestions for future talks or future presenters, now would be a great time to just shoot something quick in the that chat box. We're getting people saying thank you very much for your presentation, and thanking you for the follow-up questions. And so we'll wait just a second to see if anybody wants to suggest topics or presenters.
Sure. If I can also thank all of your audience. It was extremely interesting and informative questions. So I appreciate the audience as well.
Yes.
And I thank you and obviously Nicole and Abby and Eric for making this work.
Yeah, Abby's our tech person, and Nicole and Abby work together. So, so thank you very much, everybody, for joining us tonight. And we will see you next time, hopefully for the third talk that we're going to be presenting in partnership with the Idaho National Laboratory. Have a lovely evening, and thanks again.
Take care. Bye.